Hello, everybody. In this video, I want to show you a topic that I was thinking about, and I said I would share it with you. So the question is this: if I have a cantilever beam with a uniform load on it and all the material and geometry properties like E and I, they are constant, then we want to add a support, in this case a roller, somewhere along the beam to reinforce it. And you might say, like, where? So let's say you have a balcony or a shelf or something, and there is some load on it, in uniform load, or it could be just due to the weight of the material itself, right? So you have this balcony, and here it is basically attached to this wall. So it's a fixed support, and you want to basically put some kind of support here, right? You see many of them go with some angle bracket like this, or a diagonal member to reinforce it. So the question is, if I want to add a fixed point here by adding some kind of support, where do I put that point? So what? So I can either minimize the maximum deflection in this new beam, or the integral of the deflection squared. And you might say, where does these two come from? Well, why the maximum of the deflection in the beam you want to minimize that? Why? Because you know that right now in the beginning, before any support, the shape looks something like this, for instance. And then when you put that support in, the shape will be different, right? So you might get something like this. And so the maximum deflection in the beam will change. Right now, here on the left, this could be your Y maximum. But when you put that support somewhere along the way, now this might be your Y maximum, right? Or maybe it's on the other side. So here the Y maximum changes, and as you know, the stress in the part is related to this Y. The further the part deflects from its original position, the further the stress in the beam is going to be, and that means basically the beam is more prone to breaking. Now, of course, in this case, if you want to look at high stress points, not only you have to look at this Y maximum point, or the point where the M actually becomes max, not just Y. And the other thing is, you might also need to look at these critical points as well. Okay, so that's one thing. Now, again, the stress, if you remember, sigma equals negative my over I. So sigma max is at Y max, and this Y max is different from this Y max, because in some solid mechanics book, this Y is called delta. So Y max here depends on the cross section and the distance from the top or the bottom of the beam from the neutral axis. That is really Y max, which could be a constant number in this I. So really maximum stress happens when the bending moment is maximum, not Y is maximum. As you know, M is proportional to Y double prime. So really the place that the curvature is maximum is where stress is max, not where Y is. But of course, Y maximum has limitations too, because you don't want, for instance, your balcony to go more than so much down, because it can affect the structures underneath it, or there is a limited space underneath it or above it for basically deflection. So one of the measures that you can have is to minimize the maximum of Y, or again, if you want, you can minimize the maximum of Y double prime, for instance. Another way you can look at it is, instead of just looking at a single point where the deflection becomes maximum, you can look at what? You can look at the entire beam. So if at any arbitrary position X now, this deflection, as I said, this deflection is Y, you want to minimize the whole deflection all over the beam. So it's not just that point, any other point is also important. And since some of these Y's are positive, some of them are negative, you're going to square all of them and you're going to integrate it over the entire beam, and you try to minimize that. So as I move this roller to the left and right and I get different shapes of beams, I want to see which one of them has a kind of minimum total deflection all over the beam as opposed to only at a single point. That's where I integrate the y squared from 0 to L. Okay? So these are the two cost functions that I said, or we can come up with this one, a third cost function, or any other cost function. And the goal is the A here, the location of the support, is my variable, and my cost function is any of these, and I want to find the best location to put my support right there. So here, the way to go about it, if we, let's say for instance, we want to find this one or this one, the first thing we want to know is y. What is the deflection at any point along the beam if the support is placed at a distance a from the left side? So we show that deflection function by y of x and a, where ax is the input and a is basically another input, but you can call it also a parameter of the function. And so here we can use superposition. We can say this scenario here is like the cantilever beam plus what? Plus the, which is subjected to the a uniform load, and it's also a cantilever beam which is subjected to a vertical force reaction at the roller. We can call it R. Okay, so here if I add these two scenarios together, that is going to be this real case scenario. And if I assume the deflections are not really big, I can use superposition. I can find y as a function of x and a, and then what? I can calculate my cost function. So first I look at the scenario that you only have a uniform loading and nothing else. And here, as you know, the bending moment at location x under uniform load is going to be WL minus x squared over 2. And you can just look at your solid mechanics, right? If you want, you can look at your solid mechanics books or tables. So if you know in this cantilever beam, this W is the load per length, okay? It's a load density. So the equivalent of that is going to be like WL here in the middle. So the shear force, the reactions at this cantilever is WL, and then this bending moment is going to be WL squared over 2. So now if you're going to cut it at a distance x, at that point, if you look here in the middle, you have the load WX, and these distances are x, each one x over 2. And at that cut here, you're going to have the bending moment M. And if you take some of the moments about this point or any of these points, you can clearly, by summing the moments of these three forces along with M, you can clearly find that the bending moment at that cross section is this. The other thing you have is at point 0 on the left side, y is 0 and y prime. The deflection and the slope should be 0. This is the condition for cantilever beam. So now with that, we know that M is equal to EI y double prime. So that's what you do here. And now I divide both sides by EI, or I can keep EI on the left side. I integrate both sides, okay? And once you do that, you can find your y prime, integrate it again, you can get y, and make sure you apply these two boundary conditions to find your constant. And once you do the double integration, applying boundary conditions, this is gonna be your deflection as a result of only uniform load, okay? And you can see in the textbook tables at the end of solid mechanics books, this formula is provided. So you don't need to go through all this derivation. You can directly read it off of those tables. And then if I have a load somewhere here in the middle at the distance A, correct? So if I have a load like R, I can also do a similar procedure and find the y as a result of that. And the y here is going to be basically a piecewise function, because between 0 and a and between a and l, the bending moment will be different. So here, between 0 and a, you're going to get this cubic function. Between a and l, you're going to get this line function. Again, this result is available at the end of solid mechanics textbook, and you can just go and grab it directly. So now, based on superposition, the total deflection is going to be the deflection because of W, which is downward, and the reflection because of R, upward. So if I subtract these two and I say my y is downward, then y of W minus y of R is going to be the downward deflection, which is going to be this piecewise function. So between 0 and a, this one, right, this fourth degree polynomial, and between a and l is the other fourth degree polynomial. Now that we found it, can I plug it into either this one or this one and do the optimization? Not yet, because they are both involving a parameter r that we don't know yet. We say the reaction at the roller is r, but how is r related to everything else? So one thing we have to do is, we know at x of a, since we have a roller, the deflection should be 0. So we use what we call the compatibility condition. And at x of a, we set it equal to 0, and we can find the basically reaction at a. Now that I have this, I can go ahead and plug it into these formulas. Now my y is going to be what? Is going to be a perfect formula in terms of W, L, and X. Okay? Now that there is nothing ambiguous in it, now if I want to find the y maximum, the first cost function, I have to see where this function can be maximum. Now clearly this is a piecewise function, so I have to look into the maximum over the first range and maximum over the second range. So what I need to do is to take partial of y with respect to x for both the range between 0a and between a and l, and because the function is continuous in each range, you see it's just a fourth order polynomial, and there are 2 points that are also need to be considered. One of them is the end point here, okay, which is outside the range of the two, and the other one is the pivot point here, okay, because that is where the function changes. So these 2 points should also be considered. Clearly at x of 0, the deflection is 0, it's minimum. It can never be a y max. So what I'll do, I consider these 2 critical points as well as the points at which the derivative of these functions are 0. And then between these points, I'll see y is max at which one of them. And when we say max here, we are talking about the absolute value of y, because y here is clearly negative, so we look at the absolute value of it. Now, can I find an analytic formula for that? No. Why not? Because you can see that here, these functions are fourth order polynomials, right? So when I take derivative of y with respect to x, I'm going to end up with cubic polynomial. One here and one here. And can I solve a cubic polynomial in general perfectly analytically? Well, it's not really necessarily super easy. There might be solutions, but here we typically solve them numerically. Okay? So this is if you want to do it with respect to what? With respect to maximum y. And you might say, how do you determine a now? Well, remember that your function y, if you look at it, your function y is a function of a. So when you take partial of y with respect to x and set it to 0, whatever solution that you will find, whatever x star, which is the location of the max you find, it is going to be a function of a. And when you plug it back into the function, your y max is also be a function of a as well. Okay, so clearly they do depend on a. So now the question is, now I have a function of a. Now I need to change a and see how this function, which is a function of a, this y max, how it is changing as a function of a, so I find the best a. Because remember, my goal is to find the best location for a. So here is basically a search, right? It's a search problem over different values of a and over different values of x. It needs a nested for loop, basically. The other one is integration. So you basically integrate this total y, square it, and you have to integrate it separately between 0a and l. Again, plugging these functions here will make this j to be a function of a, and again, if you can do that, in this case it's integral, so you should be able to do it, but you need to now take the derivative of this cost function with respect to a and set it to 0. And the problem is, again, this is gonna be a high degree polynomial in terms of a, and the solution of that has to be done numerically. So it's better to basically do a numerical optimization, and you can do a brute force search, you can do any type of numerical optimization and find the best location for the support. And here in this MATLAB code that I wrote, you can change your L, you can change your EI or flexural rigidity, you can change your density of the load, you can let your A to change here. I let A change from the very almost left side to the very almost right side. I don't go all the way to the left side, and I don't go all the way to the right side. I just go in basically all of this range except for a little bit to the left and right off. And then I use 100 points, different locations for A over a span of, let's say, 1.5 meters. And if you want more accurate results, you can search over more A's. And then to perform my integrations and to find my derivative of y with respect to x, set it to 0, I need a bunch of x values. And here I use 400 x values along the beam. And you see here, this cost function stores the value of y maximum. This cost function stores the value of integral of y squared over the whole beam. And you see here, I'm using a loop over a loop over x, and I'm storing everything and then using my min functions for max y and for the integral function, and then showing you the results. As you can see, if I look at the normalized coordinates, for maximum deflection, the best place was about 0.286 of the length, and for the overall integral of the deflection, it was about 0.277. And these two numbers are very close to each other. Okay, so if I want to know which point is really the best point in this case to put my support, it's a little bit over. If I make this guy in 4 pieces, it's a little bit past basically what the quarter of the beam, 0.27, 0.28. That is the best place if you want to minimize the total basically deflection or the maximum deflection. Again, if your goal was to minimize the maximum stress, you could just look at the y double prime and you could try to minimize that. Okay, so, and y double prime, you can see in this case is this quadratic function over EI. So hopefully this video was useful to you and you can learn something from it, and I'm gonna give you the access to this code so you can play with it and learn from it, and I'm gonna see you in the next video. Thank you.